Hello students, welcome back to session 10 of Banach spaces class. So in this class, let us discuss about the conjugate space X star and its dual also. So we know that the conjugate space or the dual space X star of the nonlinear space X. Okay, you know that the dual space X star is also a nonlinear space. What it contains? It contains set of all functions f from x to k which are linear as well as which are continuous. So they contain continuous linear transformations, therefore it's called functionals. So X star contains set of all f from x to k which are linear as well as continuous. Okay, so we know that this is also a nonlinear space. Okay, now let's consider the dual of this space X star. The dual of X star is denoted by X star whole star, or this is equal to X double star. X double star. What X double star contains? It contains set of all transformation T from where to where? X star to K which are linear as well as continuous. So now X is the nonlinear space, X star is also nonlinear space. In fact, X double star is also a nonlinear space. They contain the linear functionals on X star. Okay, therefore this belongs to X double star, and each vector X belongs to X. Each vector X belongs to X gives rise to a functional, say fx. Instead of t, I will write fx because corresponding to x we have a function fx, okay, which belongs to X double star. For each x belongs to x, we have a functional fx belongs to X double star, and there is an isometric isomorphism of x into X double star. There is an isometric isomorphism of isometric isomorphism of x into X double star, called the natural embedding of x into X double star. That we will prove it in this class. Okay, let's take up this. So suppose X is a nonlinear space. X is a nonlinear space, and then each vector x in X induces functional fx on X star, such that fx of f, that mapping I will define by fx of f is f of x, because fx of x is definitely it lies in k, which is a scalar field, and f is also a mapping from x to k, so it is also a lies in k. Therefore the mapping is well defined. Fx of f is equal to f of x for every element f belongs to X star, means for every functional f, and norm of fx is equal to norm of x. So if x is a nonlinear space, then each vector x in X induces a functional fx on X star, such that fx of f is equal to f of x for every f belongs to X star, and norm of fx is equal to norm of x. Further, the mapping T from X to X double star, such that T of x is equal to fx for every x belongs to X, defines an isometric isomorphism of x into X double star. Okay, this mapping, the mapping T from X to X double star is an isometric isomorphism of x into X double star. This is the thing that we are going to prove it in this class. First, let us show that fx is a function on X star. Means fx is a function on X star means fx is an element of X double star. So when fx lies in X double star, if it is linear as well as continuous. First let us take up fx is linear. For this I will choose any two elements, say f and g, to be any elements of X star, and alpha comma beta be scalars, and we consider fx of alpha f plus beta g. Fx of alpha f plus beta g is, according to our definition, alpha f plus beta g of x. So since this can be written as this is equal to alpha into f of x plus beta into g of x. Alpha into f of x is fx of f plus beta into fx of g. Therefore, we can show that therefore we have fx is linear. Next, let us come to show that fx is a continuous or bounded. Say let us take up this. Now fx is continuous. Now for any f belongs to x star we have, for any f belongs to x star we have fx of f is equal to what? By definition mod of fx of f is f of x, but f of x, you know that this is less than or equal to norm of f into norm of x, that we have proved already. So you call this as number 1. Now f is bounded because it is a functional, linear functional, so this is bounded. Since f is bounded, we can see that fx is also bounded. Fx is bounded means it is continuous. Therefore, fx is linear as well as continuous means fx is a linear functional on x star, means fx belongs to x double star. Okay. Next condition is we need to show norm of fx is same as. Now we need to show norm of fx is same as norm of x. Norm of fx is same as norm of x. Now we have norm of fx is what? By definition supremum of fx of f such that norm of f is less than or equal to 1 by definition of a norm. So this is definitely less than or equal to supremum of norm of f into norm of x. Just now we have shown fx of f is less than or equal to norm of f into norm of x by 1. So this is less than or equal to norm of f into norm of x such that norm of f is less than or equal to 1. So this is equal to norm of f is less than or equal to 1 means supremum of these values means it is less than or equal to norm of x. Therefore, we have shown norm of fx is less than or equal to norm of x. You call this as number 2. Now we need to prove the reverse inequality, that is norm of x is less than or equal to norm of fx. So for this, let's look at this. If when x is 0, if I take x to be 0, what will happen? If I take x is 0, then the inequality is trivial because norm of x is 0, fx of f is f of x, that is also becomes 0. So let x be non-zero. If x is non-zero, then we know that if x is a non-zero vector in a norm-linear space x, then by Hanbank theorem there exists a functional f belongs to x star such that f of x is equal to norm of x and norm of f is 1. Okay, but norm of fx is what? Supremum of fx of f such that norm of f is equal to 1 by definition of equivalent norms. Okay, so this is equal to supremum of mod of f of x, fx of f is f of x such that norm of f is equal to 1. So this and also norm of x is what? Mod of fx, which is f of x is equal to norm of x. According to this, norm of x is mod of fx, which is less than or equal to supremum of mod of f of x such that norm of f is equal to 1. This is always true. So but this term is nothing but norm of fx by this condition. Therefore we can see that norm of x is less than or equal to norm of fx. So 2 says norm of fx is less than or equal to norm of x, and 3 says norm of x is less than or equal to norm of fx. Therefore from 2 and 3 we can conclude that norm of fx is equal to norm of x. So one part of the proof we have proved. Now let us come to other part. Other part is we need to define the mapping T from x to x double star such that that mapping we need to show it is an isometric isomorphism. So I'll define a mapping T from x to x double star by T of x is equal to fx. You know that fx is an element of x double star. So T of x is equal to fx for every x belongs to x. Now we show that T is linear. Say for this I will take any two elements, say x and y in x and alpha comma beta be scalars. Then we have T of alpha x plus beta y is what? According to f of alpha x plus beta y. But f of alpha x plus beta y of f is equal to what? By definition f of alpha x plus beta y, that is equal to alpha into f of x plus beta into f of y, because f is linear. So this is equal to alpha into f of x means fx of f plus beta into fy of f. So therefore f of alpha x plus beta y is equal to alpha into f of x plus beta into fy for every f belongs to x star. For every f belongs to x star. Therefore the above mapping is T of alpha x plus beta y is f of alpha x plus beta y. So that I will substitute these values. So f of alpha x plus beta y is equal to alpha times into fx plus beta into fy. Alpha into fx is nothing but T of x plus beta into T of y. Therefore we have shown that T of alpha x plus beta y is alpha times T of x plus beta times T of y. Therefore T is linear. Next is T is 1 to 1. So for this, let you choose x and y be any two elements of x and consider T of x is equal to T of y. If T of x is equal to T of y, then what will happen? T of x is fx and T of y is fy. So fx is equal to fy means fx of f is same as fy of f. Fx of f means fx of f means f of x, that's equal to similarly f of y. So f of x according to our condition, this is norm of x, so this is equal to norm of y. So this implies norm of x is equal to norm of y means what? X must be equal to y. Thus we have taken T of x is equal to T of y and we have shown x is equal to y. Therefore T is 1 to 1. T is 1 to 1. Next is T is an isometry. So we have norm of fx is what? By the as we have proved that norm of fx is norm of x. This implies norm of fx means what? Norm of T of x is fx. So norm of T of x is equal to norm of x. Means norm of T of x is equal to norm of x imply that T preserves norms. So if T preserves norms, so then it becomes an isometry. Okay, it becomes an isometry. Thus T defines it is an isomorphism. Now it's an isometry. Thus T defines an isomorphism of x into x double star. Okay, T defines an isometric isomorphism of x into x double star. Now note these following things. So the mapping T defined in the above theorem, okay, T from x to x double star is called the natural embedding or canonical embedding of x into x double star. X into x double star. If the mapping T defined above is onto, if the mapping T defined above is onto, then that mapping T is called the reflexive mapping. The mapping T is called the reflexive mapping and the space X is called the reflexive space. Okay. If there exists an isometric isomorphism of x onto x double star, then that mapping X is called the reflexive mapping. Then the space is called the reflexive space and the mapping is called the reflexive mapping. Okay. So let's take up this example. So you know that the space LP is irreflexive because LP, the dual of LP is LQ. So 1 by P plus 1 by Q is equal to 1 and LP double star is what? LQ star. LQ star means what? You forget about in place of P you can take Q also because 1 by P plus 1 by Q is equal to 1. Therefore LP double star is equal to LQ star, but LQ star is nothing but again LP. Therefore LP double star is equal to LP. Therefore LP is reflexive for 1 less than P less than infinity. But the space L1 is not reflexive because, so we know that the dual of L1 is L infinity, or that is L1 star is equal to L infinity and L1 double star is equal to what? According to this, L1 double star is L infinity star. Okay. If we assume that L1 is reflexive, then what will happen? L1 will be equal to L1 double star. L1 is equal to L1 double star. L1 double star is nothing but L infinity star. Okay. And now you know that L infinity is we know that if what will happen, so that L infinity star is separable as L1 is separable. So you know that L1 is separable. Okay, L1 is separable. If this is true, then what will happen? Say since we have taken, look at this. So L1 is equal to L1 double star, that's equal to L infinity star. Now you know that L1 is separable. L1 is separable means L infinity star becomes separable. If L infinity star becomes separable, as if the dual space of a non-linear space is separable, then the linear space is also separable. We have proved that theorem. According to that theorem, L infinity becomes separable if L1 is equal to L infinity star. But we know that L infinity is not separable. Okay, L infinity is not separable. Therefore, L1 cannot be reflexive. L1 cannot be reflexive. Okay, this is the theorem which defines reflexive mappings between X onto X double star. Okay, thank you.